Dear students, in today's lecture we will discuss about the three-phase systems. Today's lecture is dedicated to the introduction to the polyphase systems, or you can say three-phase systems and their advantages. So what is a polyphase AC circuit? Till now, whatever we have discussed in AC circuits, we have discussed the AC circuits with the single AC source. However, in three-phase AC circuits, we will discuss the circuits, or you can say in polyphase AC circuits, we have more than one AC source which is used in the circuits. In single phase AC circuits, we have only single alternating current or voltage. That means the circuit to which only one source is related. It will have only one voltage and one current. So it is something like this, right? Now to have one AC source, we need only one winding, right? So it is something like this, that there is a field system, north and south, and you have only one winding which is rotating between these two magnets which are generating the magnetic field. So this winding is rotating at some velocity omega, for example, and in a particular direction. The direction may be generally clockwise or anti-clockwise, right? But generally it is anti-clockwise in most of the cases. Now, there may be two cases. We may have the AC supply. The first is either field is rotating, or we can have the armature rotating. Now, what does it mean? As it is mentioned here, that the generator producing a single phase supply has only one armature winding. So it is the armature winding which has the EMF induced, because the electrical machines work on the principle of Faraday's law of electromagnetic induction. Hence, when a conductor placed in the magnetic field rotates at a particular velocity, will have certain EMF induced over it, which is given by E is equal to minus N d phi by dt, where N is the number of conductors or N is the number of turns in the coil, right? So if we have only one EMF, so that means only one armature winding is rotating in the magnetic field, or you can say that there is only one armature winding and the magnetic field is rotating. For example, there is a magnet and it is rotating. So when it is rotating, so its magnetic flux is cutting the winding, and hence we have the EMF induced over it. Either we can have the winding rotating or we can have the field rotating in the alternators, right? Now, for example, if we have two windings connected to one another, right, and then we have a magnet. So this magnet is, let us say, rotating. So what will happen? This magnet, while rotating, will cut the two windings, two conductors. So that means there will be two EMFs induced over it. This is E1, let us say, and this is E2. So this is what we call as a two-phase system, because here we will have two voltages and their two currents. So any AC system which is having more than one armature winding, or you can say more than one voltage source or current wave, is termed as a polyphase AC system or polyphase AC circuit. Now, if for example there are three windings, now these three windings are placed to one another at, let us say, 120-degree apart, and then we have the magnetic field magnet which let us say rotates. So it is rotating in this way that it is cutting all these three windings. So for example, we have the motor in which we have three windings like this. Now we have the magnet in between. So this magnet is rotating. When this magnet is rotating, it is cutting all these three windings, and hence you will have three EMFs induced here. So this is we call as three-phase system. In the similar manner, we may have multiple phase systems wherein we have more than one armature winding which is generating the EMF based on Faraday's law of electromagnetic induction. So as you can see, poly means many and phases here in this case is used for the windings. So multiple winding. A polyphase generator is the multiple phase or multiple windings generator. So this is nothing but an AC generator only, or you can say alternator. Multiple windings. So these windings need to be placed at a certain specific angle from one another. For example, if we are using a two-phase generator, so that means there are two windings. So these two windings are placed at 90 degrees from each other. And in this, what will happen? For example, if this is a winding A dash, and this is the winding B dash, for example. So A dash is, let us say, producing a voltage E1, and B dash is producing the voltage E2. So taking one as a reference, so let us take E1 as a reference. So E1 will be this. This is the voltage. So this is your E1 and omega t. Now what about the E2? Now because this B winding is 90 degrees ahead, it is 90 degrees ahead of A, so we can say that E2 is having phase difference of 90 degrees from E1, and we can say that it is a kind of either it will lead or lag the reference voltage. So let us say that it is leading. Let us assume that it is leading. So if it is leading, so it would be something like this. So that means your, because this is E2, this one, right? Now, so this is 0 and this is your pi, and this is 2 pi, this is pi by 2, and this is, let us say, 3 pi by 2. So that means your two waves, two voltages will have a phase difference of 90 degrees. Similarly, if we have three windings, so in three windings, what will happen? All the three windings will be placed at an angle of 120 degrees from each other, like this. So let us say this is a central point. Okay, so we will discuss it in elaborated way. So they will have a 120-degree phase angle, and the voltages, let us say E1, E2, and E3 are the voltages produced by each winding. So these voltages will also be having a phase angle of 120 degrees from each other. A three-phase generator. So this is what we call as a three-phase generator, where we have three windings and three voltages. So a three-phase generator produces three voltages of same magnitude, same frequency, but they are placed at 120 degree from one another. Now electrical degree here means that their voltages, which is the result of the rotation of winding in magnetic field or magnetic field cutting the windings. So these voltages will be placed at 120 degree from one another, right? So now a three-phase system is basically the most popular system, mostly used system. In our domestic use, we make use of a single-phase system, but in the industries, a three-phase system is used, and the generation of electricity is done at three-phase. It is not at single-phase. It is while distributing the electricity to domestic customers and industries or organizations, single phase and three phases then separated, or we can say single phase is derived from three phase system, right? So our purpose for this particular lecture is to understand little bit about the three phase systems and the advantages of three phase systems. So let us try to understand what is a single phase and two phase and then three phase by seeing some diagrams. As you can see, and as we have already discussed in previous two slides, that a single phase system, we have only one coil which is rotating in the magnetic field. We all know that the line of force, magnetic line of force, move from north to south, and the conductor cuts this magnetic field, magnetic line of forces, and generates a sine wave, an EMF basically. And this EMF is given by an equation which is given here, where EM is the peak value, and this is the instantaneous value, right? So similarly, a two-phase system, as you can see, we have two coils, coil A and coil B. So uh, as you can see, coil B is like you can compare here A1 and B1. So your coil B is 90-degree apart from this coil A. Coil B is 90-degree apart from coil A, and it is lagging the coil A, right? So when this coil will rotate in this magnetic field, so it will generate two EMFs, which are given by these two equations. And similarly, their waveform representation is shown here, right? So taking the voltage generated by this coil A as a reference, we can say that the voltage generated by the coil B is lagging. As you can see here, it is lagging the voltage generated by coil A, and that is also shown in the waveform. So this is a two-phase systems, right? As I have discussed previously also, we can have the uh, this is the field is static, and the coil is moving, right? We can also have the combination wherein the coil is static and your field is rotating. So right, so both cases can be there. Okay, it is ultimately the concept that the magnetic flux and conductors should cut each other, only then the EMF will be induced. Now here we have a three-phase system, and we have some animation also where you can see how this three-phase is being generated. So this is what I was talking about, that your coil is static and field is rotating. So in this diagram you can see we have a magnet rotating, and this rotating magnet is generating a time varying flux which is cutting the static conductors placed here. So these conductors are placed on the stator of the machine, and the conductors are static and field is rotating. So this field while rotating is cutting the conductors, and we have a three-phase output. Now this is a three-phase generator when we have three types of windings: winding A, winding B, and then we have winding C. As you can see here, you can compare this with in terms of C1, A1 and B1. So let us draw it here. So we have A1 here, we have C1, and then we have B1. So you can see they are at 120-degree apart from one another. If you compare it in terms of A2, B2 and C2, so it is something like this: A2, B2 and C2. So even then also we have an angle of 120-degree between the three windings, and these three windings are symmetrically placed from one another. They are rotating in the magnetic field, and they are generating a three-phase supply. As you can see here, the reference voltage, let us say the voltage generated by this A1 or winding A or coil A is EA, for example. Coil B is EB and coil C is EC. So taking EA as reference, uh, we can draw it as a reference sine wave like this, you can see here. And then after that we can draw each waveform at 120 degree apart from the second one. like B, voltage B is lagging A by 120 degree. As you can see, they have 120 degree phase difference. Voltage C is lagging B by 120 further. So it is again 120 degree phase difference, right? So this is how we can draw. Okay, now in this diagram, you can see the field is static and the coils are rotating. Now here you can see your field is rotating in both the cases here also, and the conductors are static. So we can have both the arrangements in three phase or single phase or polyphase alternate. As you can see here, like when this coil is aligned to this particular coil, so or this coil or this coil, so the magnetic flux is basically cutting the conductors, all conductors in a particular manner, and after that we have the voltage generated. You can see here, okay, this is a three-phase supply. Okay, similarly you can understand from this particular animation here, right? So you must have seen the three-phase transmission. Basically you must have seen some poles which are installed, right? So they have three lines or four lines basically, right? So three lines are for three phases and four line is basically for three phases plus one neutral. Okay, three phase plus one neutral. Now let us come to the next thing, which is the elementary three-phase alternator. So here let us try to understand a three-phase alternator in more elaborated way. As we have discussed in the previous slides that in a three-phase system, three windings are placed symmetrically from one another at an angle of 120 degrees, and the field is made to rotate. So this is an electromagnet basically, right? So by doing so, we will have three voltages of same magnitude and same frequency. And if we draw their phasor representation, so let us take the voltage generated by the coil A as a reference. Coil B is, let us say, lagging the coil A by 120 degree, and coil C is either lagging the coil B by 120 degree, or you can say it is leading the coil A by 120 degree, right? So EC is either leading EA by 120 degree, or it is lagging EB by 120 degrees. So both the statements are true, right? So the voltages which are generated here, these are the instantaneous values, right? And these are the peak values, right? So these are the peak values. As you can see that the peak values are same, they are not different, right? Because this is a symmetrical system, right? So taking EA as reference, so we have EA is equal to EM sine omega t. It is not that you have to take EA as reference, you can take any voltage as reference because this is a symmetrical system, right? So EB is, now this is the voltage B, this one, and these are the RMS values, right? These are the RMS values. Now EB, as you can see, is lagging EA by 120 degrees, right? Or you can say that EC is leading EA by 120 degrees. Or if we are taking EA as reference, so EB is lagging EA by 120 degree and EC is lagging EA by 240 degrees. So this is also true, right? Because your EC is lying here and EA is here. So this is a 240 degree phase difference. This is 120 degree. So either we can also say that EC is leading EA by 120 degree. From these two equations, we can say that EC is leading EA by 120 degree, or EC is lagging EA by 240 degrees. So both the statements are also true, right? Now, at any point of time, at any point of time, at any point of time, uh, the net value of the instantaneous voltages which are produced by the three windings is zero. So this can be proved by substituting the values of EA, EB, and EC in this particular equation, and we have got this one. So taking En as constant, common factor. So we have sine omega t minus 120 degree, sine omega t minus 240 degrees, and then applying the trigonometric rules, we will get that the resultant of all these three voltages at any instant is zero. But the question may arise that if the there is a question, if at any instant net E is zero, then how do the three-phase systems work? Okay, this is the question. Now the answer to this question is that no doubt at any instant the net voltage is zero, but they have a resultant basically. So that resultant is not zero. Okay, so the answer is all, the resultant vector is non-zero. It is non-zero. So this is something different, something else that we can discuss in further lectures. Now, there are certain things that we need to understand about, or we need to know about the three-phase systems. The first is what is phase sequence. So phase sequence is something like when we place the windings in such a way that they are at 120 degree from one another. This is, let us say, EA, this is, let us say, EC, and this is, let us say, EB. So here there may be two phase sequences. Either this is because coil A, this is coil C, and this is coil B. Either it can be, this is counterclockwise, and then we have, clockwise. So the phase sequence can be obtained by using the counterclockwise or clockwise direction. It can be A, C, B, or A, B, C. There are two phases, right? So this is counterclockwise sequence, this is clockwise sequence, right? So this is when you would have taken A as a reference. This is the reference. So the phase sequence is nothing. It is how the three voltages have been placed with respect to some reference voltage. So the reference voltage here is because EA. So with respect to EA, how EC and EB are taken. Whether EB is taken before EC or EC is taken before EB. A will remain reference. It is how you have used C and B and B and C. So this is the order of the phase or order of the voltages, right? So it is nothing but the direction of the rotation of the alternator. If the alternator is rotating in counterclockwise direction, so we will have this phase sequence. If the alternator is rotating in clockwise direction, we will have this phase sequence. Now the second thing that we need to know is naming of the phases, how to name the phases. Generally, the notation that is used to denote a particular phase is RYB. This is the standard global notation of the three phases. R is for red, Y is for yellow, and B is for blue. So you must have seen the three colored cables in three-phase systems. So three colored cables R, Y, blue represent three phases, and the neutral is represented by black color generally. There is another way of numbering them, is either we can number them as 1, 2, 3 or A, B, C. But generally the practical representation is red, yellow and blue, right? Now, the third thing that we need to understand is the double subscript notation. Now, let Coil A produces a voltage V or E A. Now, with respect to coil B, the voltage is V. Either it will be VAB or it will be EAB, or it can be VBA or EBA. So, how this? What is the meaning of this BA or AB? What is this? This is what we have to understand. Basically, this is the direction of the voltage. For example, EAB is the voltage and AB is the subscript. So this means voltage between A and B, where A is positive with respect to B. That means direction of voltage is from B to A. So this is what how we have to take the notations. Similarly, for the current, this is for voltage. For current, if Ry is used, this is if this notation is used. Now in subscript, let us take it in terms of AB. So if IAB is used, that means current is flowing from A to B. IBA means current is flowing from B to A. So this is how we have to understand the notation while analyzing the three-phase systems. So there are two things that we need to understand. The first is the direction of voltage. And the second is direction of current. So as you can understand from these points here, so these 2 points are for the current and these 2 points are for the voltages, right? If VYR is written, so we have taken RYB as the notations here. So VYR means Y is positive with respect to R. VRY means R is positive with respect to Y. So here in this case, direction is from Y to R. In this case, it is R to Y. Now for the current, the direction is from R to Y. And in this case, it is from Y to R, right? So VRY means Y to R. So, okay, the voltage from phase Y to phase R, right? So three very important things we need to understand: phase sequence, naming, and the how to understand the notations of the voltage and current. So let us come to the next slide, in which we will understand the symmetrical and balanced systems. Basically, a three-phase system is balanced or unbalanced, both. So we may have a balanced three-phase system, we can have an unbalanced three-phase system. It is desirable to have the balanced and symmetrical three-phase system. Now, what is a balanced and symmetrical three-phase system? So a three-phase system in which the voltages produced are equal in magnitude, right? So a system is said to be symmetrical when the various voltages are equal in magnitude and are displaced with one another by equal angles. So that means the construction of the winding is totally symmetric. So only then we can have the magnitude and angle displacement same in case of three-phase systems. Now the system will be balanced when the various voltages are equal in magnitude, the currents are also equal in magnitude. Now because voltage is cause and current is effect, so this means that when we are talking about a three-phase system, so current will only flow when we have a three-phase load connected to this. Only then the current will be flowing. So if this current is same, all these three currents are same, all these three voltages are same, right? We will say that the system is balanced. So symmetrical system is related to the construction of the alternator. Balanced system is related to the connection of source, the three-phase alternator to the three-phase load. Okay. Now, as you can see here in this, there are two diagrams we have shown. In the first diagram, it is representing the balanced system. So you can see that all the voltages have the same peak value, right? Their frequency is same, their magnitude is same, their RMS values will also be same. However, in an unbalanced system, you can see they have different magnitudes, they may have different frequencies, they may have different currents, right? So is matlab means EMFs, right? So EMFs currents are different. So this is what unbalanced is. So it is desirable to have the balanced system. So this is desirable, right? So advantages of three-phase system. So let us understand the advantages here. A three-phase system has many advantages. The first advantage is that any three-phase system or a machine is smaller in size as compared to a single-phase machine of the same output. For example, if the output of a machine is P, so to get this P, we when we design a single phase machine and three phase machine, so the size, so the three phase machine will be compact in design, in size and volume, right, as compared to single phase machine to get the same output, right? So we can say the volume of a three phase machine is less as compared to a single phase machine. Okay. Now, the second thing is we need, less conductor material in case of three-phase systems as compared to single-phase system. For example, if we have to draw a three-phase system using a single-phase winding, so we need like this. So this is, let us say, EA, this is EB, this is EC, this is AA dash, this is BB dash, and this is CC dash. So these are the three single-phase windings, right? And let us have a three-phase winding. So 1, 2, 3, and 4. So we have 4 wires. Here we have 2, 2, 2, 6 wires, right? So the conductor material used in single phase is more as compared to the conductor material used in three-phase systems, right? Three-phase system can set up a rotating uniform magnetic field in static windings, which cannot be done in a single-phase currents. So, okay, this means that a three-phase motor is self-starting, but single phase is not, right? So this is, we will understand in machines, right? Now, three-phase machines are more efficient as compared to single-phase machines. They give more power and they have more efficiency, more power. They have good power factor and they save more electricity as compared to single-phase machines. So it is very essential for us to have an understanding of three-phase power, three-phase circuits, so that we can compare it easily with the single phase. So the overall behavior, overall response of a three-phase system is better than a single-phase system or single-phase machines or single-phase circuits. And that is why when it comes to the high power rating or power consumption applications, we prefer using three-phase than a single-phase supply or system. So this is it for today's lecture. Thank you so much.